Hello, welcome to Flipped. Today we are on the last chapter of electrolysis, which is simple electric cell. A simple electric cell basically changes chemical energy into electrical energy, and we use two metals of different reactivity to produce electric current. Let's take a look at the diagram here. We can see something is very different about this setup. Instead of having batteries here, as in previous experiments, previous setups, we have a voltmeter now. Okay? And this voltmeter does not provide external source of energy like a battery does. So this voltmeter actually, it does nothing except to monitor this whole reaction. Okay, monitor how much current is being generated. The source of energy actually just comes from these two metals themselves. Okay, the difference between them, the difference in reactivity between them will cause a current to form. Okay, voltmeter is simply here to determine how much current is formed. So how this setup is being done is basically we put the more reactive metal on the anode and the less reactive metal at the cathode here. Okay. The anode will undergo oxidation, cathode will undergo reduction, okay, based on this sort of formula we have. ORAC, correct? Oxidation always happens at anode, reduction always happens at cathode. Okay, so this is something you remember. So let me just show you how it's happening. Okay, oxidation, okay, if I use a metal A, for example, oxidation is to release electron, so I form an A plus an electron. Reduction is to take in an electron, so I'm using a B plus ion to take in this electron to give me B solid. Okay, so this is the so they are opposite reactions. Oxidation gives out electron, reduction takes in electron. So when we talk about different reactivity, we are basing it on the reactivity series. Okay, we know that closer to the top, they are more reactive. Closer to the bottom, they are less reactive. Okay, so potassium is the most reactive, gold is the least reactive. Okay, as we move down this series here, the reactivity decreases. So the process goes like this. The electron released from oxidation is actually this guy, this electron. Okay, electron released from oxidation at the anode travels, okay, the same electron travels up the cathode via the wires. So I produce electron here, it travels up via the wires, you can see the electron flow, down into the cathode. Now the H plus is attracted to the cathode. Okay, H plus, where does it come from? Because you can see that I have dilute sulfuric acid in this solution. Dilute sulfuric acid is H2SO4, which if I ionize it is H plus and SO4 2 minus. So when we talk about this H plus, it's actually coming from here, this guy here. Okay, so H plus attracted to the cathode will undergo reduction, basically this process, with the released electron, which is the same blue guy, the same blue electron here. Okay, when this happens, oxidation and reduction are both being done, electric current is set up, okay, and can be harnessed for energy. So this is a very physics process. You don't have to know too much for regarding the physics part. You just have to know the chemistry part, which is just like this. Okay, when oxidation and reduction is being done, we set up electric current. Full stop. Okay, that's all. It's quite simple without the physics portion. So the voltage, okay, determined by the voltmeter here, depends on the difference between the reactivity. Okay, so the greater the difference, greater the voltage. What do I mean? Let me give you an example. If I were to choose two metals, let's say magnesium and zinc, for example. Okay, there's two metals in their way, right? Aluminium and carbon. Okay, there's two things in their way. So this one maybe generates a 5 volt. Okay, that's the first one. Second, okay, I want to use potassium and all the way to tin. So you can see how many things are in their way. 1, 2, 3, 4, 5, 6, 7. 7 metals are in their way. So this one has greater difference, correct? Greater difference in reactivity. This one will generate maybe 20 volts. Okay, so this is what I mean. Voltage really depends on the difference between the reactivity, how big the difference are between the two metals. Okay, and greater the difference, like this one is very small, this is very big, greater the voltage will result in. Okay, so this is what I mean. If I were to put C and A, so I have to choose one for C, one for A. Okay, the difference between them, the greater the difference it is on the reactivity series, the greater voltage I will generate. Okay, so this is the idea behind this. Let's look at an example, okay, using salt bridge. Okay, it's the same thing. Okay, in this chapter, you really have to know two things. First, is using batteries, correct? That's our usual setup. We just have to determine all the molten, concentrated, all that stuff. But now we are using voltmeter. So this is the second one. Okay, voltmeter doesn't apply. Voltmeter is its own, I would say, its own sub-chapter. Okay, you don't try not to confuse this with the one we have learned before with the batteries involved. So the only difference between this diagram and the previous one is that there's salt bridge now. So what's a salt bridge? You don't really have to know in the syllabus. Basically, they are here to balance the charges. What do I mean? For example, if there are two, for example, this solution is too positive, okay, because of some reactions going on, I can shift some negative charges over from here, the zinc sulfate one, through this salt bridge into this guy to decrease the positivity. Okay, so that's one example. If here gets too negative, I can shift some positive charge over. Okay, vice versa, both way works. Okay, so this is the idea behind salt bridge. It's really just to make sure that the charges are relatively similar on both sides. Okay, and that's all you have to know for salt bridge. Is you don't have to delve too into its technical details. Next, what we see are two metals. Okay, we will see them. We will locate them on the reactivity series later. Let me just show you something first. First, we have copper. We chose copper, but when we choose copper for the electrode, we have to make sure that we use copper 2 for the solution. Okay, this is just something to make sure that they are both same. If you use zinc as the electrode here, zinc 2 plus as a solution. Okay, so this is something to take note. When we use metal A, for example, we have to use its relevant solution. Let's take a look at the reactivity series and try and find copper and zinc. Copper is here, zinc is here. Okay, if you notice this reactivity series, there are 3 C's. 1, 2, 3. Please take note that the last C is copper. This is carbon, this is calcium. Okay, please try not to mix them up. Okay, so copper is all the way at the bottom. So we learned here that we want to put the more reactive metal at anode, the less reactive metal at cathode. So let's take a look at this one. Which is the more reactive metal based on the reactivity series? Zinc, right? So zinc has to go to the anode. Okay, so this is my anode. Whereas this one will be my cathode. So far makes sense, right? So let's try and write in their equation. Anode, okay, is the zinc, will be as such. Zinc solid, arrow to give us zinc 2 plus aqueous. Okay, and since there's 2 plus, we have to balance it with 2 electrons. So far, so good. Cathode, this guy, it's reduction. So what we have to do is Cu 2 plus aqueous. So we are talking about all this solution here to plus using these 2 electrons that we have generated at the anode to give us Cu solid. Okay, overall reaction we have learned before. Basically, we have to ensure that electrons on both sides have to match. So in this case, they do. So we just cancel these 2 out. Okay, these 2 electrons out. We look at what's on the left hand side. It's just zinc 2 plus, zinc solid, and Cu2 plus aqueous. So we just write that down. Zinc solid plus Cu2 plus aqueous. What's on the right hand side? Zinc solid, zinc 2 plus aqueous plus copper solid. Zinc 2 plus aqueous plus copper solid. So just a reminder that overall equation does not have electrons. Okay, so you have to cancel them out before you add them in, before you add the other things in. So the process for this setup is really very similar. It's the same actually as the previous one. Okay, just that a minor tweak, which we'll talk about. First of all, electrons are released from oxidation. This guy. Okay, this green electron is the same. Released via oxidation at the anode, traveled up to the cathode. So far so good. It's the same as what we have learned. Goes to the cathode here. And now, Cu2 plus, just now we learned that it's H plus, okay? Now it's Cu2 plus attracted to the cathode, okay? Because, okay, we are using copper sulfate solution here. And if you recall, okay, in our discussion for other electrolytic cells, okay, we always want the positive charge will always be attracted to the cathode, am I right? So in this case, copper 2 plus solution has copper 2 plus, of course, and H plus because it's a solution, so it has H plus. So we usually choose H plus, right? But why do we choose Cu2 plus here? is because we look at the reactivity series. Okay, copper is more readily discharged than hydrogen. Okay, if you recall, on the top, closer to the top means more reactive, but less easy discharge. Correct? It's opposite effect. Whereas near the bottom, okay, the bottom here, it's less reactive, more readily discharge. Okay, so this is the difference, okay, between H plus and copper. H plus is here, copper is here. Cu, copper, is more readily discharged. That's why we use copper in this here instead of H plus. Okay, hopefully that makes sense. So, and that's why Cu2 plus attracted to the cathode will undergo reduction, selective reduction over H plus instead. And with the released electron, which is this guy here. Okay, same dude, same electron that's being evolved from this setup, from this anode, and forms copper metal here. Okay, the observation is that you will see that copper electrode grows in size, correct? Because this is our copper electrode, it just keep adding on size. Okay, so over time, it will just form this big lump here. Okay, you cannot control how the metal will be deposited on this electrode. Okay, so it will just form whatever shape it wants to. It can form a clunky rock, for example. Okay, and this is realistically what it will form. It will not form a very nice rectangular rock. Okay, no, it will form this boulder here. So maybe I just do a quick recap here. What's going on is, okay, electrons released from anode goes up here, okay, then it comes to the cathode, and the voltmeter will give you a voltage. And at the cathode, okay, there are two kinds of ions being attracted here, H plus and Cu2 plus. But we choose Cu2 plus to undergo reduction because of the reactivity series. Cu2 plus is more readily discharged than H plus, so we choose Cu2 plus. And undergoes reduction means to take in two electrons to form Cu solid, which gets deposited on this electrode here, and that's why it grows in size. Okay, and with that, we have come to the end of electrolysis with this final subchapter of simple electric cell. Okay, stay tuned for the next chapters.